Today I'll be talking about shallow fusion, end-to-end contextual biasing. Automatic speech recognition, ASR, is an important component in speech interactive systems, such as Alexa. Incorporating contextual information or contextual biasing can improve the performance of conventional ASR model. The contextual information includes an user's favorite songs, contact names, app names. Contextual biasing, however, is challenging for end-to-end ASR model. In end-to-end model, we use shallow fusion for contextual biasing. And in shallow fusion, one represents contextual information as independent contextual language model. One can bias recognition process towards specific context by merging end-to-end models with a contextual language model. Applying shallow fusion in end-to-end models is facing challenges. One challenge is the end-to-end models prone to a small number of candidates. As a result, rare words such as song names fall off before being boosted by shallow fusion. Secondly, end-to-end models use less data during training than conventional models. As a result, end-to-end model make more mistakes on rare words. So the goal of these papers is to address the challenges of shallow fusion in end-to-end models, as well as improving the performance of end-to-end models. Firstly, to address the early pruning, the authors explore biasing at subword unit level. The author also explore applying contextual language model before pruning. And he also investigate incorporating contextual prefixes such as call or text. Secondly, the author model proper nouns by he explored various techniques to leverage large corpus of either audio-only data or text-only data. In this section, we reviewed basic concepts and previous results on contextual biasing. Conventional ASR models consist of acoustic model, pronunciation model, and language model. The main language model is trained on large amount of text data, which increases its exposures to context-specific data, such as song names. We bias the recognition process towards specific context by merging the language model and a separate contextual language model. The contextual language model is trained on contextual information, such as user contact names. And the biasing happens on the word level. Unlike conventional models, end-to-end models combine acoustic model, pronunciation model, and language model as a single neural network and predict subword units. Williams applies shallow fusion on word level, which is not effective for proper nouns because the subword units of proper nouns are likely pruned before applying shallow fusion. Conduct addresses the early pruning issue by applying shallow fusion on subword level units. The figure shows a contextual FSD for the word cat. Conduct used grapheme subword units such as C, A, and T for cat. We also use the same weight for these units. And the author also used the failure act to avoid giving weights to candidates that match prefixes instead of entire biasing phrases. The author, however, did not evaluate the entire context to ensure that biasing does not affect recognition quality if all biasing phrases are not relevant. This section is about shallow fusion improvement to address the early pruning, and anti-context. To improve the shallow fusion, first we do the biasing before pruning. We bias the word bits units to avoid unnecessary flooding the beam with lots of unnecessary words that have a partial grapheme match with the contextual FSD. And the biasing is only activated if we see their commonly used set of prefixes, such as, for example, contact request has prefix call or text. In this case, we explore the non-empty prefix and empty prefix cases, and we expect that using prefixes can be effective for anti-context. This section shows various techniques to increase the proper noun coverage for end-to-end models. So we train the end-to-end model using large amount of unsupervised data. To form the unsupervised data, we mine the utterances from voice search traffic, and we decode the utterances with a state-of-the-art conventional ASR model. We only keep the utterances with high confidence score and mainly focuses on proper nouns. And during training, we fill the batch with supervised data 80% and unsupervised data 20%. The issues with unsupervised data are wrong transcription and the limitation of alternate spellings of names. For example, Eric, and Eric are mapped to the one predicted by conventional model. So we generate the sentences with variety of proper nouns. For example, call John mobile. Then we synthesize using a concatenated voice. During training, we fill batch with supervised data 90% and synthetic data 10%. The session shows supervised training sets and 5 test sets used for evaluation. The supervised training sets consist of 35 million utterances from Google Voice search traffic. They are hand transcribed and they are distorted by adding noise and reverberation. And this training set is used to train the RNT model. Our 5 test sets consist of a voice search queries test set from Google traffic for anti-context evaluation, not for biasing evaluation. Also, the song, contact TTS, and apps are synthesized using the same voice and synthetic training data. And we use the test set for biasing evaluation. The contact reel consists of utterances from Google traffic for biasing evaluation. This section shows the results of shallow fusion improvement, anti-context evaluation, and proper noun modeling. The table shows the word error rate of shallow fusion improvement. The E0 is a grapheme baseline. The E1 is the word piece baseline. The E2 is the E0 plus contextual biasing. The E3 is the E2 plus subtractive cost. The E4 is E3 plus the word piece model. And the E5 is the E4 plus early biasing. The E5 is the best shallow fusion setup, which consists of word-based contextual model, subjective cost, and early biasing. The table shows the word error rate of the anti-context evaluation, and the E1 is the baseline. And we want to see a little degradation of other systems with biasing. So the E8 configuration has little degradation on voice search datasets and largest improvement on other biasing datasets. The E8 consists of contextual biasing, non-empty prefix, an empty prefix with lower weights. The table shows what are weight of the proper noun moduli. The EN is baseline RNNT model trained on supervised data. E9 is the model trained on supervised data plus unsupervised data. E10 is the model trained on supervised and synthetic data. The E10 outperformed the E9 on TTF datasets, but underperformed on real data. It indicates that the improvement of E10 on TTS datasets is from the matching between synthetic training data and TTS datasets instead of its richer vocal or proper nouns. In conclusion, this paper proposes shallow vision improvement for contextual biasing in end-to-end model. It get large improvement on biasing evaluation and get little degradation on anti-context evaluation. The papers also propose data creation techniques for improving the coverage of proper nouns for RNT model.